I'm not thinking. Good for you for being involved. Okay, we are live on YouTube. Say hello, everybody. Hi. How few people there are today. I guess the topic is not as gripping as I would have hoped. Or maybe everyone's logging in from YouTube to watch. I'm not sure. No one's logged in yet. So someone pointed out to me, sorry? There's a midterm tomorrow, not in this class. So what I anticipate is, like, the next couple of days, a bunch of people will find the slides. I understand. Well, that's too bad. You weren't here. So someone pointed out to me that on the homework assignment, apparently I asked you to compute Pearson's correlation, even though I said you don't have to compute Pearson's correlation. So you don't have to compute Pearson's correlation. So I guess I don't know what I was thinking when I assigned that homework thing. I think I just looked at the block in the back of the textbook. So consider it practice, but in an exam scenario, I will not be asking you to manually compute Pearson's correlation coefficient. All right, so today we're going to have another wonderfully short lecture because the thing that I want to cover is essentially one core concept in statistics. And I don't want to distract it with much other stuff. I don't want to go over too many examples. So the example that we do today is maybe challenging for some of you. If you don't get it right off, don't worry about it. The important part is that you try to grasp the concept of what I'm going to talk about, because we'll be returning to this concept later on. Now, that concept is rejection areas on a distribution and how to tell whether or not to reject an hypothesis test. That means nothing to you right now. It will in 10 minutes. Okay, so this is statistical inference, part 1. If you remember, as I mentioned several times in the opening lectures, inferential statistic is when we do things to a sample to try to figure out things about a reference population. So here's the Wikipedia definition of inference: the act of deriving conclusions from premises known or known to be true. So we have premises known to be true in our sample, and using our wisdom and statistical techniques, we derive conclusions about another population from our sample. So statistical inference is drawing conclusions from data that are subject to random variation. What is random variation? That's random variation here. I've randomly selected a sample from my large population. I'm doing things to that sample to make statistically inferential conclusions about the large population. And this is the heart of what we call frequentist statistics, and really what you will be doing with statistics for the rest of your lives if you go into any kind of research at all. So there are, in general, two kinds of ways of doing inferential statistics. They're hypothesis testing and parameter estimation. They both get you the same answer, but they're different philosophical approaches. You've probably seen a little bit of hypothesis testing in high school already, some of you, not all. And it's the way that traditionally every textbook begins with hypothesis testing, but in practice, scientists all do parameter estimation. And what that is a parameter estimation would be based upon a sample of students here. I compute your mean ages, I do some stats to that mean age, and I infer the mean age of the student population of the university. And what I've done is I've estimated the parameter, which is the mean age of students in the university, and I assign it a confidence interval. Now, I know Kahina has mentioned confidence intervals already in the lab. That's good. She started that process, and we'll go more in depth in future lectures. But all a confidence interval is it's a range in which I am confident that if I repeated this test a billion times, X% of the time, my estimate will fall in that same range. X%, usually you say 95% or 99%. Now those magical numbers should register something in your memories. 95 and 99. Remember I mentioned those numbers before? They're big because a Z value of 1.96 was 95% of everybody under the normal curve. And a Z value of, I think, 1.99 was 99% under the normal curve. So we like 95 and 99 because they're nice round numbers, and we know the Z values that correspond to that number of responses under the normal curve. That's parameter estimation. That's the idea of detecting, deriving, concluding, estimating a measurement in my reference population and assigning a range in which I am confident that my estimate probably lies. Hypothesis testing, on the other hand, is phrasing a question. Is saying, with X% confidence, do I think that the mean age of the university students is this? Okay. They kind of answer the same question, but in different ways. So we're going to do a little bit of hypothesis testing today, and later on we'll stumble into parameter estimation. So hypothesis testing is when we test an hypothesis. Yeah. Duh, there it is, right? So a hypothesis is, in lay language, a testable question. I hypothesize that if I drop this thing, it will fall to the ground and make a loud noise. Bang. I can test that. I can do an experiment to test it. So in traditional scientific research, we have research questions, hypotheses, and conclusions. So a research question would be something like, does gravity pull devices down to the ground to make loud noises? Interesting question. An hypothesis would be something I can test. If I were to drop a 2-gram device 2 meters from the ground and drop it, what's the decibel noise it will make when it hits the ground? A measurable thing is an hypothesis. So a testable question. As you progress through research sciences, you will be asked to phrase research questions and derive hypotheses that are testable under that umbrella of research questions. So a master's degree, for example, your thesis, you'll have a series of research questions. For example, are women more likely to vote conservative than men? Something like that. So how do you operationalize that? You devise a hypothesis saying, in my sample of 20 women, if asked the following question, and if voting patterns were measured in this way, what is the probability that they will vote a certain way? So hypothesis testing is about answering a testable question. A research question is the larger sort of wisdom-oriented exploration I'm making. So when we talk about hypothesis testing in statistics, however, we really only care about one really important hypothesis, and that is the null hypothesis. Who's heard of the null hypothesis before? Good, some of you have. Excellent. So I want to ask you what that is because we're going to go over it right now. So the null hypothesis, all it says is nothing's going on. Null. No response. By nothing's going on, we usually mean the rates or whatever we care about are equivalent in the two groups, in the test group and the control group. Or there is nothing to be found. Right? So we're always testing whether or not our sample deviates from the null or confirms the null hypothesis. So an example conceptually I'm going to go over right now is to consider a trial for murder. Dun, dun, dun. Right. So in order to be set free, a defendant charged with murder has to avoid being proven guilty, whether or not he or she is actually guilty. So we don't know if he or she is ever actually guilty. All we know is the jury must decide, based upon the evidence, whether or not they think this person is guilty or not. Right? So it's kind of like hypothesis testing, right? I don't know actually what the average age of students are in the university, but based upon the evidence presented in this sample, I will make an educated guess as to what that average age actually is. Right? And the degree to which the evidence is strong will determine whether or not I, the jury, decide if my estimate of the population age is correct or not. So he does not have to prove his innocence. Let's assume it's a he who's on charge for murder here. Right? All he has to do is avoid being proven guilty. Do you see the distinction? So in a court of law, we don't have this thing called innocence. We have guilt or not guilt. There are extreme cases where you can petition a court to actually say that no, I'm just not guilty. I'm innocent. It's rare, but put that aside for a second. So a court almost never says innocence. A court says not guilty. Do you see why? Do you have any idea why a court never says innocent? Always says not guilty. Do you see a difference between innocent and not guilty? What's the difference? Everyone's scared. Come on. Yeah.
Maybe there's not actual evidence-based innocence.
Yeah, exactly. So there's a threshold of evidence that we require in order to prove guilt. If that threshold is not met, then we can't say that guilt has been achieved. All we say is there is not enough for guilt, therefore there's not guilt, not guilty. We're not saying he absolutely didn't do it. All we're saying is there's not enough evidence to prove that he did it. All right, so the phraseology is important in a court of law because we're logically leaving open the possibility that maybe he did it, but we can't say that he did it. So we're still going to shun him socially. We can't punish him criminally. All right, so in other words, the burden of proof is on the prosecution to prove his guilt. The burden of proof is on the scientist to prove that an effect actually happened. So a good way to always to put this in context is to think about a drug trial. Does my drug actually work? So in a drug trial, we have an experimental group and a control group. Let's say the drug trial is, I don't know, migraine relief again. Okay, so there's always going to be some people who got better from the drug and some people who didn't get better from the drug. And maybe the proportion who got better from the drug is higher than that portion who didn't get better from the drug. And you say, okay, the drug's working. But how big does that proportion have to be? Right? So proving guilt is like proving the drug works. I need sufficient evidence to prove that the drug works. If I don't have enough evidence, I can't say the drug absolutely doesn't work. I just say, I don't have enough to say that it works. Right, so let's move on here. So a common strategy in a court of law is to try to introduce reasonable doubt to the jury. Right? Maybe, like we found him with a knife in his hand and he had the, blood all over him, and the victim was lying at his feet. But he's got a twin brother that looks just like him. Maybe it was his twin brother. Right? Is that reasonable doubt? I don't know. There's a lot of evidence to suggest that he killed the person, but now there's doubt. So the same with hypothesis testing and statistics. Look, this group here that got the migraine drug, they got fewer migraines than this group. Yeah, but it wasn't a big effect, and maybe they got better because it was a sunny day, and migraine sufferers have less migraines on sunny days. Whatever it might be. Okay, so in statistics, we have two kinds of hypotheses. We have the null hypothesis and the alternate or alternative hypothesis. I say alternate usually. So the null hypothesis essentially says that there's nothing going on. There's not enough proof that the person's guilty. There's not enough proof that the drug works. The alternative hypothesis says, oh, he's guilty, and oh, yes, that drug works. Right? The default state, there's nothing going on, there is no relationship, no effect, no guilt. That's the null hypothesis. Statistically, we tend to present this as equivalence. In the test group and the control group, there's equivalent amounts of people getting better. Even if it's not precisely equivalent, they're statistically equivalent. They're more or less equivalent. Some students have a hang-up about this. They'll do a test and say, oh, hey, I've got a group of 10 people here and 10 people there. 10 got better in this group, and only 9 got better in this group. Clearly, this group is better. One person is not a lot. Right? So you have to keep in mind that the absolute measure is not necessarily the measure that we care about. It's the statistically relevant measure. What does that mean? We'll see that in a second. So again, the null hypothesis, there's nothing going on. There is no guilt. The lawyers are pushing towards this. And the same with statistics. Statistics is pushing towards this because this is the default situation. If we have enough evidence to push it from here to there, then we know it probably is true that he did it. Our threshold is held high. Right? We want to make sure that we've done everything possible to discount this possibility. We explore every possibility to make this the case, and if we can't, then we accept this. Right? So that's because science, much like the law, is conservative. That means we make it as hard as possible to convince ourselves that something is going on. In theory. In practice, there are a lot of disreputable scientists. Some are reputable scientists who just need to publish a lot, right? Who'll find every excuse to find significance. That's not the way it's supposed to work. Much like the court of law is not supposed to work that way. We try every excuse to find not guilty. And if the evidence is overwhelming, well, I got to say you're guilty. If the evidence is overwhelming, I got to say the drug works. Okay, so we always make sure, we always assume that the null hypothesis is not false and seek to find evidence to reject this assumption. We almost never know that the null is true. I'll say that again. If the null is true, that means the guy is innocent. We never know for sure. So it is physically impossible to prove innocence. The best we can do is prove not guilty. So we never accept the null, we just fail to reject the null. The same way we never prove innocence, we just fail to prove guilt. I'll say it one more time. We never accept the null. We fail to reject the null. Some modern statisticians have started using that terminology, saying we accept the null. I don't like it. Don't do it. It's philosophically and logically wrong. We never accept the null. We just fail to reject it. Okay. So the way we write the null hypothesis in statistics is like this. H sub naught, we call that. So not 0, H sub naught. And the alternative is H sub A, or sometimes H sub 1. The textbook likes H sub A. You will see in classic statistics text H sub 1. Oh, there it is, H sub 1. Okay, so let's go back to the courtroom. So someone's on trial for murder. In order to be set free, they have to avoid being proven guilty. He doesn't have to prove innocence. He doesn't have to prove, oh, absolutely the two groups are equivalent. I just have to prove that I'm not guilty. All right, so what's H sub O here? Well, nothing's going on. The defendant is not guilty. H sub A is something's going on. The defendant is likely guilty. Okay, so that's what we're testing here. So here are the trial is like a test, a statistical test, right? So if they say that he's guilty, then they've rejected the null hypothesis, and if they say there's insufficient evidence to say he's guilty, then we say he's not guilty. They never say he's innocent. They fail to reject the null. Again, I say it again, failing to reject the null is not the same as accepting the null. The same way that not guilty is not the same thing as innocent. Does anyone not get that? It's kind of a key concept. Right? There's a logical issue here. Failing to reject is not the same thing. This is a positivist assertion that I know truth. I don't know truth. I just fail to know lack of truth. I fail to know falsity. Okay? Is failing to reject the null the same as accepting the null? No, it is not. We never accept the null. At best, we fail to reject it. However, we can accept the alternative. So here are the possible outcomes of our courtroom trial. So here we have accepting the null hypothesis. These are two scenarios which we accept the null hypothesis. In other words, we say the person is not guilty. And here we reject the null hypothesis. In other words, we say they are probably guilty. We have a verdict of guilt. And these two scenarios, if in fact he actually is innocent, this is he actually is guilty. We never know if this is the case. But let's assume there is a godlike power who knows the truth, right? So the universe, God, whoever it is, knows that he's actually innocent or knows that he's guilty. This is truth, and this is what we decide. The same way in statistics, we never know the truth. We never know if the drug actually works. All we know is our test tells us that, hey, it worked or it didn't work. Working means we reject the null. Not working means we fail to reject the null. Notice this says accept the null. That's wrong. I plucked this from a website, right? We never say that. So I'll point out that some people use this verbiage. I will not accept that verbiage. It's failed to reject. Okay, now let's look at the possible scenarios here. Let's say we acquit him. We acquit the guy. We say he's not guilty, but in fact, he is truly innocent. Yay, we win. That's great. The universe works the way it's supposed to work. Or we convict him. We say, you're guilty, you're going to jail. And he actually did do the crime. Yay, we're right. The universe works the way it's supposed to. But in these scenarios, the universe did not work the way it was supposed to. Okay? In this scenario here, we convicted him. We said the drug worked, but it doesn't work. He's not guilty. He didn't do the crime. And in this scenario, we say that he didn't do it, but in fact he did. In other words, in a drug trial scenario, we say that the drug actually works, but it doesn't. Let me ask you something. What is worse, to convict an innocent man or to acquit a guilty man? What do you think is worse? Whisper, 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 whisper. Commit, commit. Put up your hand. Commit to something. What is worse, in your opinion? Yes. Type 1. Why is that worse? Okay, so it's a value judgment. Sending an innocent person to jail is worse than letting a guilty man go free. And that's the way our criminal justice system is based. Most countries have the same philosophy because we find it to be anathema to our values. Yes?
Would the drug analogy in this case?
No, the drug analogy works exactly the same way. That's my next question. So what is worse? to let a drug that actually works slip through our fingers, or to put to market a drug that doesn't work? It's worse to put to market a drug that doesn't work, and that's the scenario here, right? So we reject the null. We say the drug works, but in fact it doesn't work. So we decide that this is a worse scenario than that. So our system, in both law and statistics, is set up so that we try to minimize this as much as possible. Unfortunately, the system also works this way. Either one of these two can be minimized, not both. The more precise I get with this one, the more I have to allow this one to be bigger. The more precise I get with this one, the more I have to allow this one to happen. So we decide in criminal law that the threshold for guilt is so high to make sure that it's very unlikely that an innocent man goes to prison. It's so high that very often some guilty people slip through. And that's the trade-off that we as a society have decided. It's the same trade-off the statisticians have decided. To make sure that fake drugs don't make it in the market, we let some good drugs slip through because the threshold for proof is so high. We call that type 1, type 2 errors. And type 1 and type 2 errors pretty much dominate the rest of frequentist statistics. It's this trade-off between these two concepts here. We have a symbol for type 1 error. We call that alpha. And a symbol for type 2 error, they call that beta. Or 1 minus beta is beta. Right. But alpha is a critical one. And alpha will come back to play a role in absolutely everything we do from here on in. Right? So type 1, conviction of an innocent person, incorrectly rejecting the null. The drug doesn't work, but we think it did. Right? The man didn't commit the crime, but we think he did. Type 2, equality of a guilty person, incorrectly failing to reject the null. Not incorrectly accepting, incorrectly failing to reject. Again, there's some logical nuances. Okay. So the choice of that's moving on to another aspect of hypothesis now. The choice of your null hypothesis is very important. It determines the kind of test you're going to make and the kinds of cutoffs you're going to allow. And directionality is important. So directionality means, do I care if the average age of my university students is more or less than this sample, or do I only care that it's different or the same? Right? Does it matter to me if it's greater versus less than? That's directionality. So here's an example. The women in this university have the same average age as the men. That's no directionality at all. Right? The women in the university do not have a higher average age than the men. That has directionality. Okay, let me say that again. Okay. I just woke up. So the women in this university have the same average age as the men. The opposite alternative hypothesis, the women do not have the same average age as the men. Does that imply any direction? No, it does not. All we care about is that they're not the same. It could be greater or less. All we care is that they're not the same. In this example, the women in this university do not have a higher average age as the men. The alternative is the woman's average age is indeed higher than the men's. Do I care about direction in this one? Yes, I do. I care that it's higher than the men's, not lower, higher. So obviously this one has more opportunities to confirm this hypothesis, because I'll accept cases in which they're all less than the men's. Whereas this one, all I care about, they're not exactly the same as the men's. Right. So how does that play into our statistics? It plays into something called a one-tailed versus two-tailed statistical test. A one-tailed test has directionality. A two-tailed test does not. We're going to see why they're called one-tailed and two-tailed in a second. So if we want to know if something is bigger or smaller than something else, we apply a one-tailed test. If all we care about is that it's different from something else, we apply a two-tailed test. Most tests are two-tailed. If we don't know, we usually assume it's two-tailed. Almost all tests are sort of pre-jigged to do two-tailed testing, because in the real world we care about differences, not direction. So a one-tailed test looks for an increase or decrease in the parameter, whereas a two-tailed test looks for any change in the parameter in either direction. So, example, the boys in class are doing better than the girls in class. Is that directionality? Does that have direction or not? Yes, it does, right? It's one-tailed. The boys in the class are performing differently from the girls. Does that have directionality? No, it doesn't. All we care about is they're different, up or down. That's two-tailed. The mean age of the class is greater than 17. Does that have direction? Yes, it does. I care about if it's bigger than 17, not if it's less than. So that's one-tailed. The mean age of the class is not equal to 17. That's two-tailed. At this point, you may be asking yourself, how does this have to do with inferences? These are samples that I've taken. What does this tell me about the larger population? Well, look at this one here. The mean age of the class is not equal to 17. What that is actually saying, and this will take a bit of mental gymnastics to wrap your head around, is my statistic, my sample is 17. I'm wondering whether the parameter from which this sample is taken, the entire university population, is not equal to my statistic. All right? This may not be obvious to you right now, but put that in the back of your mind and see if it comes up later. So anytime I'm comparing something to an external value like 17 or something like that, this is a statistic, and I'm looking for a parameter. See if my parameter is different from my statistic. So this is an example of inferential statistics. So here's an example. We want to know whether the mean age of UO students allows them to drink in the USA. And so the cutoff for drinking in the USA is 21. So we sample 100 of them and ask their ages. So let's say you're my sample. Like 30 of you here today, but let's say you're 100 of you. Okay, so my hypothesis, my null hypothesis, the null always says nothing's going on. The mean age of the university students is not different from 21. Nothing's going on. Equivalence. Right? So the null is always about equivalence. The alternative is going to be the mean age of the students is less than 21. So does that have direction? Yes, it does. I care if it's less than 21. I don't, not that it's different. It's less than. So I know right now I'm going to apply a two-tailed test. This is how I write statistically my hypotheses. My null says that my parameter is 21. That's what I'm assuming here. My alternative is that my parameter is less than 21. So again, the mean age of U of O students. That's the mean age of U of O students, my parameter. Right? So I want to see if it's less than 21. In our sample, let's say, this is my sample, I get a mean age of 22.31. This is my statistic. I'm going to do something to my statistic to estimate my parameter. We also know the standard deviation in my sample is 2.11. That is also a statistic. Remember the difference between statistics and parameters, right? So, and this is a one-tailed test. Everybody with me so far? Good. So we can perform this test at any level of type 1 error. So we always define, when we do an inferential test, the level of type 1 error that we care about avoiding. So usually we say it's 1%, 5%, or 10%. 5% seems to be the most popular. And you'll see what that means in a second. So we're going to perform this test at 5%, and that means there's a 5% chance of wrongly rejecting the null. A 5% chance of type 1 error. Crazy confusing, right? This is why I'm going slowly and doing one thing today to make sure it gets drilled home. What type of error is this? This is type 1 error, because I talked about that already. Okay, so if we perform this test at 5% level and decide to reject the null, we say there is a significant evidence at the 5% level to suggest the hypothesis is false. What hypothesis? The null hypothesis is false. Okay, alpha is 0.05. That's the way we usually write this down. 5% error in type 1, alpha is 0.05. Okay, now back to my normal curve. This is where our normal curve comes into play. Yes? Yep.
The null hypothesis was
So my null here is this, right? So, and let's be clear over here. So I go here now. If I were to select 100 students at random, like 1 billion times, I've selected you guys once, 1 billion times, and I took your mean ages. Remember the sampling distribution of the mean, the central limit theorem? The central limit theorem said that the means of samples of 1 billion samples of anything distributes like this. Right? Remember that? This is an important observation we made about binomial distributions a couple of lectures ago. Okay? So this again represents the distribution, the frequency distribution of all of the means of a billion theoretical samples that I've taken from the university. You're just one sample. If I throw you back into the pool and I pick another 100 students, take another sample, I'll throw them back in the pool, another 100 students, take that sample, and so forth, and computed their ages for each sample, and I plotted the mean age, I would find that the most of the mean ages are this much, and so forth. Once I get in this range over here, well, very few mean ages are down here. Very few. Most of them are over here somewhere. How many are down here? Well, it depends on what my cutoff is. If I say my cutoff is 5%, then I care about the 5% that are of responses that are down here somewhere. If the sample that I choose in my test falls in this range, then I'm pretty certain that it's unlikely that my sample is representative of all of these people. Right? If, on the other hand, the mean that I compute from my sample falls in this range over here, I'm pretty certain that it comes from every other, it's like every other sample that I have. Right? So I care about this. This is my rejection level. This is when I say I feel confident in rejecting the null and avoiding a type 1 error in here. So the smaller I make this area, the less likely I'll make a type 1 error. It's just harder to find that. I can make this down to like, 0.00001% down here, but I'll never get that almost. So we play with what's a reasonable amount of rejection area that we will accept. And 5% seems about right. So in a one-tailed test, we care about the 5% that are down here. Remember, I chose 5% because that's the alpha I chose. I could have chosen 1% or 10%. In a two-tailed test, I will subdivide half of my alpha over there and half of my alpha over here because I care about, is it bigger than everybody else and smaller than everybody else. In my one-tailed test, because, back here saying, I chose less than. I care if my mean is less than 21. Over here, I care if my region is in the low end. If I chosen bigger than 21, I'd care about the high end. If I chosen I don't care either direction, I would have rejection areas at both ends. Still with me, I hope. Okay. So what is this critical region? It's also the rejection region. This is, again, if my mean is rare, how rare this rare, then I feel confident in rejecting my null hypothesis. Right, now how do I figure out whether or not to reject my null hypothesis? This is where we apply our statistical tests and get these funky values that we look up in the back of tables and stuff. It gets pretty dry and boring. This is why I'm trying to go through very slowly to make sure that it gets drilled home. Right, so again, we let our alpha, our type 1 error, be 5%. So we go to our z tables. In the back of your book, you will find z tables. Or you can look up the z value in an online calculator, and I put a link on these slides. So what z value corresponds to 5% of responses? Well, minus 1.64. That means minus 1.64 standard deviations from the mean is where I begin to find this region here. If it was plus 1.64, it would be over here. Okay? Yes?
Plus 1.64, what is that?
Well, 1.64 z's is 1.64 standard deviations. So that means in my theoretical distribution of a billion samples that I've chosen from the university, 1.64 standard deviations from the mean value of all those samples, it gives me 5% of all the distributions. That's all it says. 5% of the mean, that's all it means. Okay? So here's my data again. I'm trying to figure out if the average age is less than 21. My data in my sample has an average age of 22.31 with a standard deviation of 2.11. And you remember how to compute a z statistic? Well, it's the average minus the average divided by all that stuff. That is a parameter, that's a sample. Right. It might be backwards here. No, that's right. So you plug in the numbers and we get 6.21. What do I do with that? Well, we reject our null if our z-test is less than 1.64. This is actually, right, that's right. Our z is 6.21. Is that less than 1.64? Negative 1.64? More than that? It is. It's over here. So our z's over here somewhere. I'll say that again carefully. So our z is 6.21, which means that our sample came from over here somewhere. Over here somewhere, right? Way down here. 6.21 z's from the mean. But our rejection level is down here. So that means our sample is actually well within the zone where we don't reject. We can't say that our sample represents a scenario in which we reject the null. Okay? Therefore what? We fail to reject the null. So in other words, at the 5% significant level, we cannot conclude that the mean age of students is less than 21. What we're actually saying here is when I have my sample, functionally, I'm trying to see if my sample represents the mean age of the university. What I'm actually saying is, does my sample come from the same universe in which the average age of university students is 21? That's what the math is actually saying. The math is positing that there are an infinite number of universes, and the sample that I took may be from a universe in which the average is 21, and maybe from a different universe. This statistical test tells me that there's a 5% chance that it's not from a universe in which the mean age is 21. Whew, complicated, right? Again, a lot of stuff to unpack there. If I were to do a two-tailed test, if I cared about whether or not, if I didn't care whether or not it was less than 21, only if it's different from 21, I would separate out my critical values evenly between the two. It wouldn't be 5% here and 5% there. It's 2.5% here and 2.5% there, so that I distribute them evenly. Right? So here's an example. 40 sales receipts from a grocery store has a mean of $137 and a standard deviation of 30. That's my sample. That's my statistic. Using these values, test whether or not the mean sales of the grocery store is different from 150. So this is the parameter that I'm testing to see if my sample comes from the same universe in which the mean sales are $150. That's what I'm saying. So the first thing we do is we set our null and alternative hypotheses. My null is that the mean is 150. My alternative is that it's not 150. You'll notice here I use H1 instead of HA because I'm a classical statistician. I use H1. Right? Here I have no direction. All I care is that it's different. Okay? Now this is the parameter I'm testing, so I use my parameter value over here, my parameter notation. I'm testing to see if my sample comes from a universe in which the mean is 150. So here's my test statistic. Plug in my z values. So we've got 137 minus 150, and I get minus 2. That's my final number there. What do I do with that number? Well, I go back to my distribution here. So a couple things I decide first. Is this a one-tailed or two-tailed test? It's a two-tailed test. We already said that because we don't care about direction here. We just care if it's different. So what confidence level do I want? I can choose whatever I want. But we're going to say 99% for this case. Yes? Sometimes. Level of confidence, yeah. Because all the exams are multiple choice, so clearly, you know, I'm not going to go through each one. So yeah, I'll tell you which one to choose. I may not tell you if it's one-tailed or two-tailed. You've got to figure that out yourself. And I will give you the chart in the back of the book and all that. By the way, I usually give you cheat sheets because I don't believe in memorization. So you don't have to memorize equations and things like that. I think, if I remember correctly. I get my classes kind of confused sometimes. But yeah, so don't worry about memorization. Worry about doing the thing. Okay? So if I choose 99% confidence, I'm saying that it's a 1% rejection. I'm going to separate out my 1% on both ends of my distribution here. So 0.005 plus 0.005 gives me 0.01, which is 1%. What do I do with that information? Well, I have to look up the z-score that corresponds to this. What z-score do I look up? 1 or 0.05? You'd think so, right? Depends on how the table is arranged. So we look up the table. It'll specify, is this a two-tailed or a one-tailed test? If it's a two-tailed test like this, you look up 1%, it'll give you the right z value for 0.005. The same thing with the online calculators. It does the work for you. Conceptually recognize it's already split the difference for you. Okay? And the reason for that is if you do it if you look up 0.005 in a one-tailed test, they'll give you a negative number here and a positive number there, and you've got to figure out what to do with them. So the charts do the work for you. Make sure you look up on the two-tailed section for 1%, and it'll give you the number for 0.005 at both ends. All right. So here's how it works. We now compare. We have my. I've computed a z-score of minus 2.722. So in other words, in my big distribution, right, minus 2.722 z's to the left of my mean is where my sample is. It's where my sample's over here somewhere. I can already tell it's going to be beyond this number, right? So I looked up a z-score of minus 2.58. That corresponds to my 0.005 over here, and a plus 2.58 corresponds to my over there, and I know that I just computed a minus 2.7 for my sample, so my minus 2.7 is over here somewhere. Is that in the rejection zone? Yeah, it is. So without even going to the next slide, I can already tell that, hey, my sample doesn't come from the universe in which the average samples are 150. It's different. Right? So our critical region is, we say this, the absolute value is greater than 0.258. That's the same thing as saying it's less than that and greater than that. Right? So it's basic math. Right. So there it is. So in other words, our test statistic is in the rejection zone. Therefore, we reject the null hypothesis in favor of the alternative. We conclude that the mean is significantly different from 150. Right? Thus, I have proven that the mean sales at a grocery store is not 150. I haven't proven what it is. All I've proven that it's not 150. That's all I can do. Okay. So it's important in these kinds of questions to answer the question at the end of it all. You just do the math and walk away. You have to remember what it is you're trying to compute. There's a lot of stuff to unpack here. I recognize that. So it's okay to be a little bit confused. Just give it some thought about what exactly we're trying to do. You can use this z-score calculator online. I like this one because you can pick a one-tailed versus two-tailed and see how it plays out. And I've got one big homework question here, and that's the solution, and a couple of ones over there. So try them out and see what you think. And this, the funny thing is, almost no one uses z-scores to do calculations like this. So we'll do like a couple of these in this class, and you probably never do it again in your life. We move on to other kinds of tests after this, to things like t-tests and chi-squares. Okay, good times. Traumatized. All right. At least it was fast.